Hello students, welcome to a class of topology. Today we are going to discuss about dense set in a topological space. Okay, let's see the definition. Suppose we have a topological space X2. Let X2 be a topological space. And A is a subset of X, which is a non-empty subset of X. Okay. Then we say that A is dense in X. A is dense in X if its closure, A closure is equal to capital X itself. When a closure of a non-empty set is the full set X, we say that the set is dense in X. Okay, this is the definition of dense set in a topological space. Let's see one example. For example, if you consider indiscrete topological space X2, and I denote the indiscrete topology as tau I, and let A be a non-empty subset of X, then what will be its closure, A closure? By definition we know that A closure is the smallest closed set containing A. And what are the closed sets in this topological space? But the closed sets in this topology are empty set and capital X itself. These are the only open sets and only closed sets in the indiscrete topological space. Okay, then what will be A closure? We have to consider all the closed sets which can contain A. Since A is a non-empty set, the empty set phi cannot contain the set A. So the X is then capital X is the only closed set which can contain capital A. Therefore, what will be the closure? A closure, you have to consider all closed sets containing A. Then you have to take their arbitrary intersection, or you have to take the smallest one among that. Here, capital X is the only one such kind. So, A closure will be equal to our capital X itself. What it means? In an indiscrete topological space, if you take any non-empty set, then its closure is nothing but capital X itself. So, which implies in an indiscrete space, every non-empty subset is dense. Every non-empty subset is dense in X. Okay. Now, what will happen in the discrete topology? We will see. For an example, consider a discrete topological space. Okay. X 2D. 2D denotes the discrete topology, the power set topology. Okay. Then what will be? Let A will be a non-empty subset of X. Okay. What will be A closure? In the discrete topology, we know that every subset is open. Correct? When A is a non-empty subset, then A is open and also A is closed. You have seen that every subset in the discrete topology is open. That means they are always open as well as closed. So, every non-empty set will be a closed set in the discrete topology. Therefore, what will be A closure? Closure of a set is itself when the set is closed. Since A is closed. Why A is closed? Because since every set is open in the topological space. Open means closed and open. Okay. When A is closed, its closure is itself. So, A closure will be equal to A. Correct? Therefore, if you take any non-empty subset, its closure will be equal to A. Correct? So, is it dense in X? We can say that a set is dense in X if its closure is equal to capital X. So, when you take a proper subset, its closure will be that set itself, which cannot be capital X. If A is proper subset, then A cannot be equal to X. Therefore, A closure cannot be equal to X. So which implies proper non-empty subset cannot be dense in discrete space. Only the dense subset is capital X itself. Okay, which implies A is not dense in X. So which implies proper subset in a discrete space cannot be dense in X, or no proper subset of X is dense in a discrete space. So the only dense subset in a discrete space is the full set. The full set. But we are looking for a dense subset which are proper subset of X. Okay, it's enough. We will see one more example. For example, I take a set which is a particular example A, B, C. I am considering a X equal to the three element set A, B, C, and I take tau as collection empty set, full set, and singleton A, and set AB and set AC. Okay. Now, if the topology is like this, then what are the closed sets in this topological space? Then the closed sets are collection C equal to its complement, empty complement is X, and X complement is empty, and AB the set A complement is set BC, and set AB complement is set C, and set AC complement is set B. So these are the closed sets in this topological space. Now let us take it set A equal to capital A equal to set B. Then what will be its A closure? A closure is a smallest closed set containing A. And what are the closed sets which can contain the set B? Capital X, B, C, and B. These are the closed sets containing B. And which is the smallest one among that? Smallest set is singleton B, and singleton B is the X closure. If you take A as set AB, what will happen? What is its closure? When you find out its closure, you have to consider all the closed sets which can contain AB. Which are the closed sets which can contain AB? BC cannot contain AB, C cannot contain AB, B cannot contain AB, empty set cannot contain AB, and X is the only closed set containing the whole set AB. And then capital X is the only closed set containing A. Therefore, what is its closure? A closure, since it is the only one, its closure is the capital X. When A closure is equal to capital X, we can say that A is dense in X. So here A equal to set AB is a dense subset, but A equal to singleton B is not a dense subset, which is not equal to X, which implies A is not dense. So in this particular example, set B is not a dense set, but set AB is a dense set. Next is a theorem which is a necessary and sufficient condition for denseness. Okay, theorem. A subset A of a topological space X tau is dense in X if and only if A intersection B is non-empty for all non-empty open subset B of X. So theorem says that when the set A is dense in X if and only if you consider intersection with any non-empty open subset B with A, that will be non-empty. So suppose X tau is a topological space and A is a subset of X, okay, and A is dense in X if you consider any non-empty open subset B, their intersection should be non-empty. That means there exists no open set B such that their intersection is empty. If you consider any open set B, that will surely intersect with our set A. That is the meaning A is dense in X. Okay, we will start the proof. Suppose that A is dense in X. Suppose that a set A is dense in X. we have to prove that for any non-empty open subset B of X, A intersection B is non-empty. So we are arbitrarily taking one non-empty open subset B of X. Let B not equal to empty B be an open set in X. We are going to prove A intersection B is non-empty. Okay, and by assumption A is a dense set in X. When A is dense in X, what you can write? Since A is dense in X, A closure is equal to capital X. Okay. To prove the statement, we are assuming the contradicting statement. For that, we have to prove that for every non-empty open subset B, A intersection B equal to non-empty. But now I am assuming let B be a non-empty subset which is open in X such that A intersection B equal to empty. Okay. Then what will happen? When A intersection B equal to empty, since A intersection B equal to empty, then we can write A will be contained in X minus B, correct? Okay. When A is contained in B, by the closure property of the sets, A closure will be contained in X minus B, the whole closure. What is B? B is an open set. When set is open, its complement will be closed. So when B is open, X minus B is a closed set. Since B is open, X minus B is closed. When a set is closed, its closure will be itself. Therefore, X minus B whole closure will be X minus B itself. Okay. Therefore, A closure will be contained in X minus B. What is B? B is a non-empty subset of capital X. B will be any non-empty subset of capital X such that A intersection B equal to empty. So suppose this is our set A, then B is a set, we have chosen that B is a set such that we are not intersecting with the A and B is open. This was our assumption. Now we have given that, we got that A closure is contained in X minus B. What is X minus B? Its complement. Since B is a proper subset of X, implies X minus B is also a proper subset of X. Correct? Therefore, A closure is contained in X minus B implies A closure cannot be equal to capital X itself because it is a proper subset of X. So, which implies A is not dense in X, which is a contradiction because we already have A closure is equal to X. So, which implies A is not dense in X, which is a contradiction. So which implies our statement is true. That means A intersection B not equal to empty for every B open in X. Now we will prove the converse part. Now conversely assume A intersection B is not equal to empty for every open set B in X. We have to prove that our claim is to prove that A is dense in X. That is, we want to prove that A closure is equal to capital X. But here we will prove the contrapositive statement. What is the contrapositive statement? If P implies Q is true, then contrapositive statement says that negation Q implies negation P is true. So here we want to prove that by assuming this condition, conversely assume this condition, we have to prove A is dense. So we will prove the negation Q implies negation P. That means suppose A is not dense in X, then we will construct an open set B such that A intersection B will be equal to empty. Okay. So assume negation Q. What is negation Q? Negation of the second statement. That means A is not dense in X. That is, A is not dense in X. When A is not dense in X, A closure will not be equal to the full space X. Okay. This is what I assumed. Now we want negation P. What is negation P? P says that A intersection B is not equal to empty for every open subset B of X. Then what will be negation P? Negation P will be there exists an open set B of X such that A intersection B will be equal to empty. So we are going to construct an open set. Okay. To prove negation P, I take B as, let B equal to X minus A closure. Why X minus A closure? Actually we want an open set. We have A closure now. What is A closure? A closure is a closed set. So if you want to construct an open set, we are just taking the complement of the closed sets we have now. So we are considering X minus A closure. I chosen B as X minus A closure. Since closure of a set is always closed, since A closure is always closed, its complement X minus A closure is always open, and that is B. So which implies B is open. B is an open subset in X. Okay. Since A is a non-empty subset, we have assumed that A is a non-empty subset. Okay, then otherwise this all cannot be possible. And since A is non-empty, A closure is also non-empty. So which implies B is also non-empty. So B is a non-empty subset in capital X. Now what will be A intersection B? Consider A intersection B. A intersection B is X minus A closure. What will be their intersection? A intersection X minus B closure. Okay. I can consider this as, this is our A. And what is A closure? A closure is the smallest closed set containing A. Then what will be X minus A closure? X minus A closure will be the complement of the set. Okay, suppose this is our capital X. Then this area will be the X minus A closure. You can clearly see that A intersection with the X minus A closure is always empty, because we can't intersect these two disjoint sets. Clearly A and X minus A closure are disjoint sets, therefore their intersection is always empty, which is equal to empty. So which proves the theorem actually. So what we have assumed? A is not dense in X. What we get now? A non-empty open subset B with the property that A intersection B is equal to empty. So we get the negation of the statement P. Therefore P implies Q is also true. So what you can say that for every B open in X with the B intersection A or A intersection B not equal to empty implies A is dense in X. So which is a very important theorem in the denseness of set in topological space. Now using this theorem we can prove that set of rationals are dense in usual topology of real line. So we will prove it as a question. The set of rationals dense in rationals Q is dense in real line with the usual topology. I denote usual topology as tau u, where tau u is the usual topology on R. Okay. So theorem says that when you want to prove a set is dense in a topological space, you just want to prove that it will have a non-empty intersection with the all non-empty open subset of the topological space. Okay. So I am considering an arbitrary open subset B of X. Here the set A is Q. Okay. Let B be any non-empty open subset of R in the usual topology. Open subset of R. Okay. So actually we need only want to prove that Q intersection B is non-empty. Okay. Now since B is an open subset, if you take an element small x in capital B, then what is B? We have B is an open subset of real line. That means B is a member in tau u. Then when you have an element in tau u and small element x is belongs to B, then by the definition of the usual topology, there exists some r greater than 0 is that interval of the form x minus r, x plus r will be contained in B itself. Okay. Now, which implies there exists some r greater than 0 is that the interval of the form x minus r, x plus r will be contained in B itself. And it is clear that x minus r and x plus r is an interval in real line. Suppose this is x here, x minus r and x plus r, then it surely contains at least one rational number. So it will be intersection with the q will be non-empty. When this neighborhood itself can intersect with the q, then B intersection q is also non-empty. So which implies q can intersect with any open set, non-empty open set in this topological space. So by the theorem, q is dense in X, dense in R by the theorem. Similarly, we can say that R minus Q, set of irrationals, is also dense in X, dense in R. Also dense in R, because by the same argument of the proof, every interval of the form x minus r, x plus r will intersection with r minus q is non-empty. So that r minus q with the B intersection with B will be also non-empty. So which implies r minus q is dense in R in this topology tau u. So real line has a countable dense set as well as the uncountable dense set.